Okay, we're starting here from Irving Langmuir again. There are a couple I wanted to read more into. I don't know how long this will be. Um, I'm kind of just going to go until my roommate comes back inside because, like I said in the previous video, it's just weird if I'm talking. Well, it's weird if I'm talking to the computer doing the, I'm still self conscious about making videos. And also, it'll just be noisy. Anyway, from Irving Langmuir to Ernst Lamp. Um, I wanted to go to Globar. This is a short one. A globar is used as a thermal light source for infrared spectroscopy. The preferred material for making globar is silicon carbide that is shaped as rods or arches of various sizes. When inserted into a circuit that provides it with electric current, it emits radiation from 2 to 50 micrometer wavelengths via the Joule heating phenomenon. Globars are used as infrared sources for spectroscopy because their spectral behavior corresponds approximately to that of a Planck radiator, a blackbody. Alternative infrared sources are Nernst lamps, coils of chrome nickel alloy, or high pressure mercury lamps. The technical term globar is an English portmanteau word consisting of glow and bar. The term globar is sometimes used synonymously in English, um, which is an incorrect spelling in the strict sense. The American Resistor Company in Milwaukee, Wisconsin, had word and lettering Globar registered as a trademark in a special decorative script font with the United States Patent and Trademark Office on June 30th, 1925, registration number 02000201. And on October 18th, 1927, that's unimportant. The registration had been renewed for the third time in '87 by various companies throughout 60 years. Let me see if I can get a Globar image. Um, okay, you get the gist. It is literally just a silicon carbide bar. Must heat up. Here's a nice picture. Aluminum sprayed hot zone overall length. Yeah, interesting stuff. There's one heated up. Okay, yeah, that it looks very hot. How about that? Cool. Let's get back to. I'm trying to kind of hop to it. Come on, back. Okay, what else to cover? Oh, for whatever it's worth, Irving Langmuir, born Brooklyn, died Massachusetts at 76. I don't think I ever really said that in his dedicated video. Um, yeah, I wanted to look at Langmuir waves and this. I don't actually know adsorption. That's new to me. So Langmuir adsorption model. The Langmuir adsorption model explains adsorption by assuming an adsorbate behaves as an ideal gas at isothermal conditions. So let's look at what an adsorbate is first. Adsorption, oh snap, this is a long one. Okay, maybe one day I'll do a longer video on this whole article, but for right now, let me just skim it. Adsorption is the adhesion of atoms, ions, or molecules from a gas, liquid, or dissolved solid to a surface. Okay, easy enough. This process creates a film of the adsorbate on the surface of the adsorbent. And if you are listening and not watching, this is adsorb, not absorb. It's ADSORBENT, adsorbent and adsorbate. This process differs from absorption, in which a fluid, the absorbate, is dissolved by or permeates a liquid or solid, the absorbent, while adsorption does often precede absorption, which involves the transfer of the absorbate into the volume of the absorbent material. Alternatively, adsorption is distinctly a surface phenomenon, wherein the adsorbate does not penetrate through the material surface and into the bulk of the adsorbent. The term sorption encompasses both adsorption and absorption, and desorption in the reverse of sorption. So sorption, Just sorption, the root there, is a physical and chemical process by which one substance becomes attached to another. Cool. And desorption, I'm guessing, is how they are removed. Like surface tension, adsorption is a consequence of surface energy. In a bulk material, all the bonding requirements, be they ionic, covalent, or metallic, or of the constituent atoms of the material are fulfilled by other atoms in the material. However, atoms on the surface of the adsorbent are not wholly surrounded by other adsorbent atoms, and therefore can attract adsorbates. The exact nature of the bonding depends on the details of the species involved, but the adsorption process is generally classified as physisorption, characteristic of weak van der Waals forces, or chemisorption, characteristic of covalent bonding. It may also occur due to electrostatic attraction. The nature of adsorption can affect the structure of the adsorbed species. For example, polymer physisorption from solution can result in squashed structures on a surface. Okay, physical adsorption is physisorption, a process in which the electronic structure of the atom or molecule is barely perturbed upon adsorption. And chemisorption is a kind of adsorption which involves a chemical reaction between the surface and the adsorbate. Okay, and just going kind of quickly here, the adsorption of gases in skipping over some stuff. Adsorption of gases and solutes is usually described through isotherms, that is, the amount of adsorbate on the adsorbent as a function of its pressure if gas or concentration for liquid phase solutes at constant temperature. The quantity adsorbed is nearly always normalized by the mass of the adsorbent to allow comparison of different materials. To date, 15 different isotherm models have been developed. So from Freundlich, the first mathematical fit to an isotherm was published by Freundlich and Kuster in 1906 and is a purely empirical formula for gaseous adsorbates. And we have x over m equals kp to the 1 over n, where x is the mass of adsorbate absorbed, m is the mass of the adsorbent, P is the pressure of the adsorbate. This can be changed to concentration if investigating solution rather than gas. And K and N are empirical constants for each adsorbate pair at a given temperature. The function is not adequate at very high pressure because in reality, x over m, that being adsorbed and mass of adsorbent, respectively, has an asymptotic maximum as pressure increases without bound. As the temperature increases, the constants K and N change to reflect the empirical observation that the quantity adsorbed rises more slowly and higher pressures are required to saturate the surface. Langmuir. Irving Langmuir was the first to derive a scientifically based adsorption isotherm in 1918. The model applies to gases adsorbed on solid surfaces. It is a semi-empirical isotherm with a kinetic basis and was derived based on statistical thermodynamics. It is the most common isotherm equation to use due to its simplicity and its ability to fit a variety of adsorption data. It is based on 4 assumptions. The first, all of the adsorption sites are equivalent, and each site can only accommodate one molecule. 2, the surface is energetically homogeneous, or homogeneous. I don't know how to say it in this case. I feel like it can vary in physics. And adsorbed molecules do not interact. 3, there are no phase transitions. And 4, at the maximum adsorption, only a monolayer is formed. Adsorption only occurs on localized sites on the surface, not with other adsorbates. These 4 assumptions are seldom all true. There are always imperfections on the surface. Adsorbed materials are not necessarily inert, and the mechanism is clearly not the same for the very first molecules to adsorb to a surface as for the last. The fourth condition, which is only a monolayer is formed, that fourth condition is the most troublesome, as frequently more molecules will adsorb to the monolayer. This problem is addressed by the BET isotherm for relatively flat, non-microporous surfaces. The Langmuir isotherm is nonetheless the first choice for most models of adsorption and has many applications in surface kinetics, usually called Langmuir-Hinshelwood kinetics and thermodynamics. Okay, here we're getting to the physics. Langmuir suggested that adsorption takes place through this mechanism. A sub G plus S, I actually don't know this symbol, I'm sorry, is equivalent to, I guess, A times S, where A is a gas molecule and S is an adsorption site. And I'll say, if you're not watching this, the equivalency sign that I'm looking at here is it's like an equal sign, but with the top is an arrow pointing to the right and the bottom is an arrow pointing to the left. I don't know that. I'm sorry. The direct and inverse rate constants are k and k sub minus 1. If we define surface converge theta as the fraction of adsorption sites occupied, in the equilibrium we have capital K equals k over k sub minus 1 equals theta over 1 minus theta times p, capital P that is. Or, I gotta go. Bye.